All right. Any questions on Verilog Lab 7, stuff like that?
Just Verilog in general. So in 270, we're going to be using assembly code. Is it going to be pretty similar to Verilog?
No, Verilog is like nothing else, and we really don't do anything else that comes even remotely close to being like Verilog. Assembly language is like programming in C, but you have to tell the computer every single thing you want it to do. So it's a genuine programming language. Verilog is really kind of a unique thing that we do at the end of 250, and then we don't really encounter again. Unless you're a double E student, and then in some upper level courses you'll probably see it again. But yeah, nothing to do with 270. 270 is a combination of assembly language programming, machine language programming, which is writing programs comprised of ones and zeros, so very low level, and circuit design, right? Figuring out how to interface a microcomputer with switches and lights and motors and timers and things like that. So in an in-person class, it would have a lot of working on protoboards and building circuitry, and I don't know to what degree we're going to do that in 270 online, because Tinkercad doesn't understand the processor that we use, which is called the PIC processor. But yeah, good chance you'll never see Verilog again for at least a few years.
Well, I'm trying to go into electrical engineering. Is it a possibility that I'm going to see it in the future?
Yeah, if you're double E, you'll probably encounter it again, because this is where most circuit design is done, and it seriously does take a while to get the hang of Verilog, right? If this is the first exposure to it, whatever you got out of it, whatever level of understanding is probably good, right? It will help the next time that you see it, and the next time after that, and eventually at some point it may start to actually make really good sense. But I wouldn't worry about it if it's still really kind of fuzzy and blurry and you're not sure what's going on. That's absolutely the typical experience. Okay, it's something that takes multiple times. It's like KVL, KCL, and 120. Right? Almost nobody understands that the first time they encounter it. Almost nobody really understands it the second or third time they encounter it. I learned KVL, KCL in 1980. When I started teaching at Clark, that was when I learned KVL, KCL. Right? All the times I had encountered it between, seeing it in school and starting teaching, it made a little more sense, it made a little less sense, right? And it really wasn't until I sat down and I started trying to explain it to other people, suddenly I actually understood what KVL, KCL was. And Verilog is very much the same way, right? So if you're asking out of concern for, I don't really get this, is that a problem? I say, no, don't worry about it. If that makes sense.
I guess it's just something to get used to, maybe later on in the future for sure.
Yeah, because it is different. It's describing circuitry, and the syntax is so confusing. But when I write Verilog, I only use a tiny little piece of what the language actually supports. And I'm honestly amazed that I was able to write this code here and have it compile. That's a bit of luck and a bit of having done similar things before. But if you don't do this every day, it's going to get stale. And these days I do this once a year, which is for 250. I used to do it on more of a regular basis in my own life. Yeah, don't worry about it, right? Whatever level of understanding you have will get built on top of the next time you encounter it, and the next time after that. And this is how we learn these things. Make sense?
Yes, sir.
All right. So, question from someone about going over compressed K-maps. We have not done compressed K-maps, and you're not responsible for those for the exam. We did do compressed truth tables, and I can talk about those a little bit. And you've actually been using them when we're doing state machine type stuff. The idea of a compressed truth table is, imagine a function of 3 variables.
Professor, we can't see anything if you're writing something.
You can't. I'm not sharing my screen, am I? How's that? All right, thank you. So imagine a function of 3 variables, and you know, whatever your outputs might be. We can re-envision this truth table as a function of 2 variables, for example, just A and B. And we fill this in, but instead of having just zeros or ones in here, we might have more complex expressions. So for example, if A is 0 and B is 0, that's these first 2 rows of the truth table. Well, in this case, F is 0, in this case, F is 0. So we can absolutely say if A is 0 and B is 0, F is a 0. But if A is a 0 and B is a 1, right, F could be a 1 or it could be a 0. So how can we describe the value of F since it changes? Well, if we look at the value of C, we can see when C is a 0, F is a 1. When C is a 1, F is a 0. So apparently in these 2 rows, F is just the opposite of C. So I can say here's the value of F in that case. And in these 2 rows, A is 1, B is 0, F is always a 1. And in these 2 rows, A is 1, B is 1, F is always a 0. So this is a compressed truth table. And we would say we compressed this original truth table around the variable C, which means we got rid of it from the inputs, and now it can appear potentially in the outputs. And we've done this kind of thing when, for example, we describe a toggle flip-flop. And we say, what's the new value of Q going to be? Right? And if T is 0, the new value of Q is the old value of Q. If T is 1, the new value of Q is the complement of the old value of Q. And if we didn't compress, we could do something like this. Right? If T is 0, then our value doesn't change. If T is 1, our value toggles. Right? But this is easier to read once you know what it's saying. Right? This is just saying, hey, the output's either the original output or the complement, depending on the value of T. This one is a good old-fashioned pure truth table, but it's not as obvious what's going on here. We need to sort of mentally change it into this. So we've been doing these compressed truth tables in talking about states. All right, and then a question about fuse maps. So programmable devices come with a picture, a template that looks something like this. Suppose we have 3 inputs, A, B, C. We have a series of wires coming across here, each of these going into an AND gate symbol. And the outputs of those cross over with a series of wires going into OR gate symbols. Which can be called whatever. And the idea is the way that we draw circuits in 120, or that we went over in this course, was to, run our wires vertically, invert their values, run those vertically, and then just connect them over to a series of AND gates, and so on, to make our drawing neat, right? Well, a fuse map basically realizes that concept in hardware. And so the idea is this symbol here, which is not a valid logic symbol for wiring diagrams, but we can use it in fuse maps, okay? It's a shorthand for, here's a wire coming down and here's an inverter going like that, okay? If you're drawing this yourself in a wiring diagram, do that, okay? But for a fuse map, and a fuse map only, we're allowed to use this shorthand notation. And this is a shorthand for saying we've got, 6 wires coming into a 6-input AND gate. Wiring diagram, draw it like that. But on a fuse map, we draw a single wire, and we understand there's multiple wires here. Same thing down here. We'd have, potential large number of wires going into an OR gate. But for a fuse map, we just draw this shorthand version. And then we draw typically a circle or an X or something to show where we make connections between vertical and horizontal wires. So as it is, when 2 wires cross, there's no connection implied. So if we wanted to implement a function like f equals, a, b, c bar, or a, b bar, we could say, well, we need to generate this product term, a and b and c bar. So let's take a, b, c bar, and let's AND those together. So this first AND gate is a, b, c bar. We also need to generate the product term a ANDed with b bar. So here's a, here's b bar. Let's feed those together into an AND gate. This is a, b bar. And to generate f, we need the OR, the sum of these 2 terms. So let's take these 2 product terms, put them into this OR gate. There's a fuse map that gives you implementation of this function f. And if you wanted to do g equal to something else, right, you can do the same process for g. And if g also needed to use a, b bar, right, we could use this same line in, another sum term. So you can reuse these things. And there's different types of programmable devices. There's PROMs, PLAs, and PALs. And it has to do with, can we control the connections here? Can we control the connections here? And in some cases, some of them are hardwired, and in some cases, they're programmable. All right, question about gray code. So how do we count in binary? Usually like this. Because if we convert each of these to a weighted sum, we get 0, 1, 2, 3, 4, 5, 6, 7. Right, this is 6 because it's 2 plus 4. This is 1 plus 4. This is 1 plus 2, and so on. That's the sort of most natural way to count in binary, but it's glitchy. Because, for example, when we go from a 3 to a 4, all 3 of these bits are changing value. And unless they change at exactly the same time, this count is going to go from, say, 3 to 7 to 5 to 4. Or maybe it'll go from 3 to 2 to 0 to 4. Right? So there's lots of intermediate values that can potentially cause problems when we have things like state machines. So a gray code is a way to go through all combinations of, say, 3 bits, such that when you move from one combination to the next, only 1 bit changes. And so a typical way to do this would be like this. Right, so we still have all 8 combinations of 3 bits, but as we go from one combination to the next, a single bit changes. And so we don't have this potential glitchiness of intermediate values. And this is called a reflective gray code because if you look at these 2 least significant bits, they are mirror images of each other. Right, 0, 0, 0, 1, 1, 1, 1, 0. Whereas with our traditional ordering of bit patterns, if you look at those 2 least significant bits, they go like this. They repeat. So we have this pattern of 2 bits, and then we repeat that pattern of 2 bits, and the bit in front of it changes. Here we have a pattern of 2 bits, and then we reflect that pattern of 2 bits. We write it backwards, and the bit in front changes. So that's gray code.
Can we go over binary arithmetic?
Sure thing. So when we write integers, positive integers, in binary we're using weighted positional notation. So we think of powers of 2. Right, where 1 is actually 2 raised to the 0 power. This is 2 to the 1st, 2 squared. This is 2 to the 7th. And when we write a number down, it's a series of 1s and 0s. And so this is the number 43 because it's 32 plus 8 plus 2 plus 1. Okay? And it's important to remember this is exactly what we do with decimal numbers, except we're using powers of 10 instead of powers of 2. But when we write down a number like, 503, we're thinking of, 1, 10, 100, and 503 is 5 times 100 plus 3 times 1. In binary it's easier though, because when you multiply something by 1 you just get that number that you're multiplying, and when you multiply something by 0 you get a 0. So here we're just adding up the powers of 2. In decimal we're adding up the digit times the corresponding power of 10. Okay, the reason that's important to keep in mind is because it means that the things we do to do arithmetic on decimal numbers also work for binary numbers. So this is the number 43, and the number 17 would be something like 16 plus 1. And so if I want to add in binary, I do the same thing I do with pencil and paper for decimal. 1 plus 1 is 2, right? Which is kind of like 10 in decimal, right? We don't write down a 2, which looks like this. We write down the least significant digit, and we carry the most significant digit. So that's our 2 right there. 1 plus 0 is another 2, so there's our 0, and we carry the 1. 1 plus 0 is 1, with no carry. 1 and 0 is 1, 0 and 1 is 1, 1 and 0 is 1, and these are 0. And so 0, 0, 1, 1, 1, 1, 0, 0. Well, that's 32 plus 16 plus 8 plus 4. That's 48. That's 56 plus 4 more is 60. This is equal to 60. Well, that's 43 plus 17. So we can do addition the way we add plain old decimal numbers. And then the more complicated part is when we get to negatives. So negatives work in a particular way. With decimal numbers, we do something weird with negative numbers, right? If we want to do negative 17, what do? We write a 17 and we put a symbol in front of it. And to us that means, hey, that's negative 17. Well, you know, this isn't a digit. We can't multiply this by a power of 10, right? It's a notation. It means if I do 43 plus this thing, I should actually do 43 minus that thing. And we can do that in binary too. We can just have a symbol which says, hey, this is a negative number. But we do something different. We do what's called the 2's complement. So in 2's complement notation, if I want to find negative 17, I do the following. 17 equals this. Toggle all of the bits. Add 1. That's how we're going to represent negative 17. All right, why do we do this? Because if we do this, our addition still works. So I can write down 43 again, which was 0, 0, 1, 0, 1, 0, 1, 1. And let's just add these together. So 1 and 1 is 0, carry the 1. 1 and 0 and 1 is 1 and 1 and 1 is 3, you know, which looks like this. So I'll write down that least significant bit, and I'll carry the most significant bit over to here. 1 plus 0 is 2, so that's a 0, carry the 1. 1, 1, 1 is 3, so that's a 1, carry the 1. 1, 0, 0 is 1, with no carry. 1 and 1 is 2, that's a 0, carry the 1. 1, 1, 0 is 2, so write down the 0, carry the 1. 1, 1, 0 is 2, so write down the 0. And there's an extra 1 coming out, but since we're using 8-bit numbers, which I didn't say, but we're using 8-bit numbers, we ignore that last carry. Well, what is this equal to? This is 16 plus 8 plus 2, that's 26. Well, guess what? That's equal to 43 minus 17. So by expressing negatives using 2's complement notation, we can do addition and it will add negative numbers correctly. And that's pretty much all there is to dealing with binary addition and subtraction arithmetic.
Can we do an example with the negative output?
With a final answer that's negative?
Yes.
Sure. So let's do, since we've already got negative 17 up here, let's just do 7. Alright, that's the number 7. Let's subtract 17. So 17 is 1, 1, 1, 0, 1, 1, 1, 1. That's negative 17. So let's add those together. So 1 and 1 is 2. That's a 0, carry the 1. 1, 1, 1 is 3. So there's a 1, carry the 1. There's another 3. 1, 0, 1. That's a 2. So that's a 0, carry the 1. 1, 0, 0 is 1. 0 and 1 is 1, 0 and 1 is 1, 0 and 1 is 1. So this is the binary representation of 7 minus 17. Okay, but we can't see what this decimal value is by just adding up powers of 2, because if we did that, it would be 2 plus 4 plus 16, 32, 64, 128. We get some big, huge number, and we know we should get minus 10. Okay, when we're converting a number from binary to decimal, we need to look at this most significant bit. If it's a 0, then we're okay just adding up powers of 2. So if the most significant bit equals 0, add powers of 2. If the most significant bit is equal to 1, then we need to do the following. Take the 2's complement, which will give us a positive number, add the powers of 2, and then put a minus sign in front. Alright, so here's our value for 7 minus 17. It's got a 1 in front. Let's take the 2's complement. How do we do that? Toggle all of the bits, add 1, gives us this number. Add up the powers of 2, so that's 8 plus 2, which is 10, and then put a minus sign in front. That's what this number is equivalent to. I'm going to put a period there so we know this is a decimal number that just happens to have just 1s and 0s. So this is equal to negative 10, which it should, because that's 7 minus 17. But all of this, it's really important if you're told you're working with 8-bit numbers. 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, 8 bits everywhere. Even though I can write the number 7 like this, if I start trying to mix that with negative numbers, I'm going to get the wrong answer. Right? So even though that's the value of 7, spell it out to 8 bits. Alright, does that make sense?
Yep.
Cool. Other questions? So there's a list on Canvas that I think covers most of the stuff that we've gone over. So we started with the idea of digital versus analog, right? Digital, we think of things as like 1 and 0, true and false. Analog is like ECS 120, where we have voltages, and they can, vary to pretty much any value. Not just two values like 0 volts or 5 volts. Binary numbers we just did a pretty good synopsis of, so positive, negative. We mostly deal with 2's complement, but we could put a negative sign in front. So we might say that if you want negative 7, just write out the bit pattern for 7, but make that first bit a 1. Right? So that's what we call signed magnitude. And our range of numbers that we can represent, let's say we have 4 bits. If I'm just doing plain old positive or 0, if I'm not worrying about negatives, I can go from 0, 0, 0, 0 to 1, 1, 1, 1. This takes us from 0 to 15. But if we're doing 2's complement for negative numbers, we can go from 0 up to 7, but then when we go to this is actually negative 8, and this is negative 7, and this is negative 1. So in this case, our range of values is negative 8 up to positive 7. So unsigned, 0 to 15. signed -8 to 7. It's still 16 different numbers we can represent, but we've kind of slid our starting point backwards, right? And instead of going from 0 to 15, we're saying let's go from -8 to +7. And the importance of using all bits, that's the thing I just said. Make sure if it's an 8-bit thing, you're using 8 bits. If it's 4 bits, you're using 4 bits. I think everybody knows how to convert from decimal to binary. We've done that a bunch of times. From binary to decimal, that's just adding up powers of 2, and then from binary to hex, group yourself into groups of 4, and write a symbol for each 4-bit chunk. Binary to octal, break your number into chunks of 3, right, starting from the least significant bits, and write a digit corresponding to each 3-bit chunk. Representing characters in binary, that's typically ASCII code, right, and it's just one of many mappings we can have to say, here's a set of bits, I'm using this to represent the letter A or the letter Q or an exclamation mark. It's nothing magic, it's just a convention. Alright, we talked about addition and subtraction. We have not really talked a lot about overflow, and that's not going to be on the exam. It's talked about in the text. But how do you detect when you have an overflow situation? And basically, if your sign bit changes, when you add 2 positives, if you get a negative number, you've got an overflow. We talked about gray code. We haven't really talked about binary coded decimal, so that will not be on the exam. But the whole idea is it's another way to code numbers into binary. So if I want to code the number 1, 2, 3 in binary coded decimal, what I would do is I would use 4 digits for each of these. I would write the number 1, I would write the number 2, I would write the number 3, and this 12-bit number represents the decimal number 123. It's not a weighted positional notation anymore. This is not 1 plus 2 plus 32 plus 256, right? It's a digit, a digit, a digit. But it's useful sometimes. It's useful with fractions, with things that have, non-zeros to the right of the decimal point, because we can avoid a lot of errors that we would get otherwise with weighted positional notation. But that's not on the exam. You got that for free, though. Make sure you know how to wire switches. Make sure you know how to connect LEDs. Okay. Switches pull up through a 1K resistor to 5 volts. Use a switch to pull it down to ground. And LEDs, typical forward orientation, run it through a 1K ohm resistor, connect the output to ground. Or you can put the 1K back here. This is coming from your circuit. Alright, if you don't do this, the LED gets very, very bright. The LED will probably pop and it won't light up anymore. The thing that's driving this circuit may be damaged, and you potentially create a short from 5 volts to ground, which can affect the behavior of the whole circuit. Okay, if you don't have this resistor here, because you basically got a straight path. So you always put a 1K resistor in series with an LED when we're doing output. Alright, you know about logic gates, AND, ORs, NANDs, NORs, NOTs, XORs, XNORs. We know how to go from a truth table to an equation. We can do sum of products, we can do product of sums. And once we have an equation, we can sketch a circuit. We can start with a circuit, we can write equations for outputs based on inputs, and then from those equations we can fill in a truth table. So both of those directions. System diagrams, which basically show you inputs and outputs to and from a circuit without looking at how the outputs are generated or the inputs are treated. It's just what goes in, what comes out. We didn't do a whole lot of theorem proving, but there's theorems we can use, like A ANDed with B is the same as B ANDed with A, or De Morgan's theorem, which you should always know, to turn one expression into another expression. So a theorem might be, this equation is the same as that equation, And we can confirm that if we can apply these equivalences, like De Morgan's theorem, to the first equation and turn it into the second equation. A more direct way is to make a truth table for each equation. And if the truth tables are identical, then the equations are the same. Alright, sum of product, product of sums. There's the normal form where we write out something like, you know, F equals A B bar C, or A C bar, or A bar B, or, you know, A B C, right? So if you're asked to produce a sum of products, this is the kind of thing you're after. If you're asked to produce a sum of products in compact form, then we can say something like F equals sum of, you know, 5 comma 4 comma 12, or whatever. All right, and the product of sums is the dual to this, where we have, you know, F is something like that, where each term is an OR, and you put all of those through an AND. All right. If you have a compact expression and it has MD, those are don't cares. Okay. Compact form uses min terms and max terms. Min terms and max terms just run sequentially through the truth table if you're ordering your inputs in the usual way. Okay. It's a shorthand, so we don't have to write out, you know, A, B bar, C. We can just say this is min term 5. Right. Minimizations, we didn't do systematic algebraic reduction SAR, okay? We minimized using K-maps. So make sure you're comfortable with K-maps. Copy your ones and your don't cares if you're doing a sum of products. Copy your zeros and don't cares if you're doing a product of sums. Okay? And then cover those entities where the dashes can be optionally covered. Cover them with as large rectangles and as few rectangles as possible, and then write the product or sum terms corresponding to each of them, and then take their sum or product. Alright, don't forget to wrap around the edges, include your don't cares if they help, don't include them if they don't help. NANDs and NORs are computationally complete, so we can build any circuit out of just NANDs or just NORs. And you've done some homework problems on those and so on. Other logic blocks, muxers and demuxers. A mux takes many things and reduces it to one. So a typical multiplexer circuit is something like a series of inputs. And we can choose one of these to be sent to the output. A demuxer takes a single input and farms it out to one of a number of outputs. And we did a lot of discussion and work with these things. Muxers, for example, we can build big muxers out of little muxers. We can also use these to implement arbitrary logic. If we have a 4-to-1 multiplexer, and I set up my inputs to be hardwired to 1101, and I think of S1 and S0 as coming from AB, I've just built a circuit to implement the following truth table. Right? Because if A and B are both 1, and I haven't labeled these, but the usual way. This is input 0, 1, 2, 3. If A and B are both 1, what does this circuit do? It takes input 3 and sends it to the output. Well, since input 3 is hardwired to a 1, if A and B are both 1, the output will be a 1. If A and B are 1, 0, input 2 gets copied to the output. Since input 2 is a 0, my output will be 0. So by just taking my inputs and hardwiring them to these bit values, I've built a circuit that produces the truth table. And I can do that for any pattern of 1s and 0s that I want. Nothing magic about this one. 7447, that's the 7-segment decoder, which you've worked with a lot. We did not talk about priority encoders, so I won't put that on the exam. But we'll probably talk about that in Engineering 270, because they're part of the PIC processor that we'll be using. There's a number of topics in the book for 250 that we'll actually talk about in 270. For example, floating point representation of numbers in binary. That'll be a 270 topic. All right, programmable logic, PALs, PLAs, proms, fuse maps, half adder, full adder, right? So you had a lab on this, you had homework questions on this, and we were just doing this a minute ago when we were doing binary addition. Right, what was I doing here? I was putting 1 and 1 into a half adder, right? I had no carry coming in. I produced a sum bit and a carry bit. And then I took these 3 bits, this was a carry in, A and B, and I put those into a full adder in my head, and I produced a sum bit and a carry bit. And that carry bit that I produced from this full adder is the carry in for the next full adder. There's the carry in, there's A, there's B, it produces a sum bit and a carry out. So making an adder out of a series of full adders, that's pencil and paper arithmetic. Okay. All right, and then we get to the non-sequential circuits, combinational circuits versus sequential. Combinational is all of this stuff, and it's a circuit that you can basically describe precisely with a truth table. Sequential circuits, you also need to know the history of the circuit. So they work because of propagation delays, because when you change the input to an inverter, the output doesn't change immediately. It takes a few nanoseconds to respond. And we can use that to our advantage and make a feedback circuit. A pair of inverters with the output feeding the input will hold a bit value for us. Okay? We can analyze these with timing diagrams. You've done timing diagrams. I'm not going to ask you about glitches. Okay, we've talked a little about them, but I'll stay away from that. But we can use these propagation delays to create latches. So a set-reset latch, a data latch, and we can use those to create edge-triggered devices, which we call flip-flops. Okay, and we're doing that so that we can control when things are recognized. So we can have all of our propagation delays and glitchiness and so on. But once enough time has passed that everything is settled, now we can trigger a clock, and all of our flip-flops will say, hey, what's on my input? And it'll look at the input and it'll remember it. And as soon as the flip-flop remembers its input value, it's going to change its output value, and that's going to start a whole cascade of changing values throughout the circuitry. But the clock has already ticked, so nobody's going to pay attention to what's happening until the next clock tick. Okay, so we're using edge trigger devices basically so we can make glitch-free circuitry. Alright, so edge trigger devices, these are called flip-flops. There's a data flip-flop, a JK flip-flop, a T flip-flop. I won't ask you about SR flip-flops. Setup and hold time, these are timing requirements. Setup says we have to have the input stable before the clock ticks. Hold says we have to have the input stable after the clock tick. We can also have presets and clears, and those could be synchronous, meaning they only take effect when the clock ticks, or they could be asynchronous, meaning they take effect immediately. Alright. If you don't remember the truth table for the JK flip-flop, put it on your note sheets. Alright, don't trust memory. Because yeah, I won't give it to you on the test, so write that down. Most everything we've designed has been synchronous. We can also do asynchronous logic where we don't have a clock. It's a lot harder. Okay. Finite state machines, so you've seen the basic picture a bunch of times. It's flip-flops, and then it's combinational logic, and there's a feedback path. Okay. There's a max frequency, which is dependent on the setup and hold times of the flip-flops and the propagation delay of that combinational logic. Alright, we have state diagrams that let us show how the system changes from one state to another. The transition arrows are usually tagged with input values, and maybe tagged with output values, or the outputs could be in the states. Depends if it's a mealy machine, where the outputs depend on the inputs, or a Moore machine where the output only depends on the state. So two different ways to show outputs. And then we spent a bunch of time analyzing finite state machines, basically going from a circuit to a present state, next state table to a state transition diagram. And the other direction is synthesizing, so starting with a state diagram, going to a transition table, going to a circuit. Alright, and then the last topic is Verilog, and we've been talking about Verilog for a couple of weeks. Basic concepts, okay? I'm not going to ask you some complex circuit. I'm not going to ask you something like a 5 of 16 event detector, okay? But you know, write Verilog code to make an exclusive NOR of 3 inputs, or write Verilog code to detect when 2 inputs are the same, or write Verilog code to implement a JK flip-flop, or counter that counts from 5 to 11 and then back to 5, right? So think homework problems, right? I won't ask you to implement a traffic light controller, but do you know how to use the module statement to describe a module, list the inputs and the outputs, wire versus register, using the assign statement outside of an always block, using this symbol inside an always block, setting up an always block to say when some event occurs, usually an edge of a clock, and then, if necessary, basic if-then structures. If up down's equal to 1, set count equal to count plus 1, things like that. Okay.
Just curious on for the Verilog part. Say we wrote down like not exactly the correct code for the Verilog. Is there partial points for it, or how would it be graded at?
That's a good question. So I haven't decided if I'm going to have any fill-in-the-blanks that get graded manually. I might do that, and if I do that, then yeah, there would be partial credit. But I may show Verilog code and ask you to pick the one that does something, or I may ask you, you know, what this particular set of Verilog code does, or I may have a fill-in-the-blank, and I'll grade it manually. I haven't written the exam yet, and I probably won't until the weekend, so we'll see. But if it's not something where there's partial credit, my hope is to have enough questions that, you know, if the code is wrong, it's like 5 points or 4 points or something like that. As opposed to, you know, here's a 20-point Verilog question and either get it right or wrong. That's not going to happen. Alright, so I think the additional course notes says 4 pages double-sided of notes, something like that. Make yourself some good note sheets, right? I'm obviously not going to look over your shoulder and see if you got 5 pages instead of 4 or something. But don't rely on your textbook, okay? You don't want to spend your time flipping through 100 pages of somebody else's notes trying to find answers. So make yourself, you know, a good note sheet of the things that you feel you need written down to help you memorize, or you just don't want to worry about memorizing, right? And try to be tactical about that. What if we redo the homework just because? I mean, the homework is really good sample problems to work on, absolutely. Go back and do the solve problems since you have the solutions, but don't look at the solutions until you've done them. That's pretty good practice too. So the final exam will be on Tuesday, starting at 12 o'clock, and it'll be an hour and 50 minutes. Okay, and that should be on here, June 16th. Alright, I have office hours at 3 today, I have office hours at 3 tomorrow, and that's it for office hours. So come find me during those times if you have questions or things you want to work on. Otherwise, congratulations, you've made it through all the material for Engineering 250. which is quite an accomplishment. So we'll get through the final exam and then go on to 270 in summer if that's what you're scheduled for. And 270 is a fun course, so it'll be a good time. All right. Have a good rest of the afternoon. I will see you next time.
Have a great day.
Thanks. You too.